Wow. Oops. So I'm going to manually put the equation in, just in case you don't like the whole y1 weirdness that I did. You don't have to do that. So 1140.4, I think that's what it was, plus 17,600.5. Let's see if I got that in there. Oh, scheisse. So I haven't done Zoom 9 yet, I guess. There we go, Jeff. So if you hit graph and nothing happens, do Zoom 9. I just forgot to tell my calculator to find the data. So that looks pretty good. Yes? So now if you do Zoom 9. Did you calculate it? Is that what you're asking? Yes. It's second quit. Second move. To quit. Yeah. Alright, now hit stat. Calc. With the line in it. Number 4. Yeah, and then you have to calculate. Let's see. And then your R, you only have to do this once, and then I'll show you what you're doing. So now you can put the, write this down, here's the slope and intercept, get y equals and put it in. Go to calc. Makes sense. We're going to calculate something. Go to calc. And then we'll the line there. Yeah. Well, no, you have to hit number 4. Yep. Go all the way down. Calculate. Yeah, bam.
I know. Is that weird or what? They're brothers. Those are Mike's best friends. But they just need to make
Another reason why I have you come up and show me this stuff in your calculator is I can quickly find errors for you. That's the worst thing in the world to put all this data in. If one thing is off, throws the whole damn thing to shit. So I'm going to help you find that real quick. That's not a reason to make a bad grade. It's because your fingers were good. Everybody does that. That's why I make so much money working from home, inputting data. Everybody doing all right? Finish it out though. You guys, I know you guys. Do the rest of those.
So this part here, if I got 0.48 for an R, I'd have to say there's no correlation. I don't see evidence of correlation. So then I would trust the line 0. I wouldn't use it. If I get 0.483, I would use the line, but how much do I really trust it to be accurate? Not that much. But it's better than just guessing the average. We got 0.808. What does that mean? Yeah, there's decently strong correlation. What kind of correlation? Positive. What does that mean about the line of best fit? And I love that question because you're like, what the shit do you want from me? But do we trust the line of best fit or not? Yes, we trust it. It is tight to the data.
Yes, we trust
It's tight. Does it make sense? It's tight to the data. Tight to the data. And then this guy, you could either do it by hand. Now, I constructed my equation based on percentages. I didn't make decimals. So if I wanted to use a line of best fit to predict, what would I put in here? 34.6. I love it. So normally in most mathematics, if you have a percentage, you've got to make it a decimal before you use it. We constructed the damn equation. I can make it do whatever the shit I want to. And I want it to use percentages. So I made it so that it can. There you go, math. And then plus this. And whatever you get. Plus 17,650 cents. I love it. Pew! So I get 57,058.34. Why do I say compared to Virginia? What is it about Virginia? Why did I pick that state? Because it has that. How did we do with the prediction? Yeah, it's pretty close. I mean, come on. If I just said, Wyoming, what's their median income? You would guess something that was nowhere near right. If I use the equation and the line of best fit, I get decently close. If you were within 2,000 of the median income of some random state, I'd go like, what the shit? Holy crap. That's good. Why isn't it, like, better? Why isn't our prediction better? What was our R value? 0.808. For it to be perfect, R would, of course, have to be 1. Yeah, so it's not really, it's not 1, so it's not going to be perfect, but it's going to be decent. It's a decent estimate because it was a decently strong correlation. The closer R is to 1 or -1, the more accurate the predictions will become. This is 0.8. That's really strong correlation, don't get me wrong, but that's why it's like a couple thousand off, but that's still pretty damn good. Right? If I said, guess how much money I make a year, and you came within $2,000 of the right answer, I'd be like, holy shit. Good job. Even though there's a website that lists all of our, every public employee, all our incomes out there. It's kind of freaky. Okay. So here's the key thing. Do your results mean that if you got more people in a state to earn a bachelor's degree, then the median income will definitely increase? Does it mean that? Hell no. Of course not. Holy shit. Correlation does not mean causation. That's a big phrase that's thrown around. It doesn't mean causation either. We just can't say. So will that happen? If you say no, you're wrong. If you say yes, you're wrong. The correct answer is maybe. That's not what the purpose of this test is. This just shows there's a relationship. Who affects who? Or is there a certain third thing that affects both? I don't know. I just know right now there's a relationship. I'd have to go a little deeper with them. Was this really a hard test to do? Did this take forever? No. So of course the results are not going to be like strong. But they do point to a relationship. Which kind of of course it makes sense. you kind of knew there's going to be a positive. You have more people with bachelors, you would expect that state to have a higher median income. That only makes sense. But it's not perfect. Why is it not perfect? Because there's other variables. What if you're in a state where there's no high-tech jobs at all? Okay, how good of a degree you get, you're not going to be making that much money. It's just the way it is. With me? Maybe? A little bit? Okay. Okay. So. You're supposed to be who knows? Why or why not? Correlation does not imply causation. Maybe if I paid everybody more, they'd have more money to go to school and get a bachelor's degree. Maybe that's the actual way this, or maybe it's a little bit of both. They affect each other. Okay, maybe. All right, so here we go. We're going to get into some really freaky shit now. All right, guys, I want to remind you of a few things about the distribution we know best. We're about to learn a completely different distribution today, and you're like, I don't like that phrase, Jeff, but it's true. What distribution am I talking about? What distribution do we use the most? Distribution. Yeah, normal distribution. What governs the shape of this distribution? Like, what I mean is, why is this one so skinny and that one so fat or fatter? Anyway, I didn't mean anything, sorry.
How spread is it out?
Good. How spread out it is, and what, of course, measures how spread out. No, what measures how spread out data is? Standard deviation. I love it, right? Right? I'm not saying anything new. It's like, well, duh, Jeff. Which one would have a bigger standard deviation? Which one has a bigger standard deviation? First one. Why? Because it measures how spread out. Which one's more spread out? This dude's more spread out, right? Sorry, dude. Feel a little. He's a little. Get out. All right. Yeah. It's Jabba the Hutt. Today we're going to learn the real Jabba the Hutt distribution. It's going to have a body and a tail. So if a normal distribution shape is governed by a standard deviation, and what do we use a normal distribution for? This is kind of funny. What could these represent? Look at everything that I plotted here. What could they represent? Give me a situation that might lead to this picture. Like this person right here. Can you come up with a situation? What? Say, all right, cool. I like it. Beautiful. I like it. That person, maybe this represents heights. And that person I just circled is taller than most people. I like it. Because he's above the halfway point. Are you with me? So maybe this represents individual people's heights. Or maybe this represents sample means of heights, right? Or maybe this represents percentages. We use the normal distribution for percentages too, right? We did a hypothesis test for a percentage. And what did you use? Z-scores, normal distribution. Oh shit. So this picture represents the distribution of heights, weights, percentages, whatever the shit we're doing, right? And the shape of it is governed by the standard deviation. All right. And you're like, yes, Jeff. That's what we've been doing. Good. That's the way you should be. We're about to talk about a distribution that would represent what standard deviations themselves look like, how they're spread. I really want this understood. So how could I create a picture like this? I could take a sample of 10 students and get their average height and plot it, and get another sample of 10 students and plot that average height and keep going. Right? That's how I create this picture. But I could create a different picture based on, let me take a sample of 10 students and get their standard deviation of their heights and plot it. Get another group of 10 students, get the standard deviation of their heights and plot it.
Not the mean, but
Yes, I'm plotting the standard deviations. So what's going to govern the shape of that? Not the freaking standard deviation, because that's what the shit's in there, right? So it's not going to look the same. In fact, here's a freaky thing. One freaky thing is, this distribution is called the chi-square distribution. Oh, Jeff. Why? Okay. This picture exists on its own, right? I mean, this, and then it could have several things. In fact, each of these guys could have a z-score, but how many formulas do I have that lead to a z-score? Several. I got this one. I've got this one. I got all kinds of freaking z-score formulas, right? But they all relate to the same picture. This looks like a Dr. Seuss bus right now, but oh. This picture exists on its own. And then I can use it in several different ways, just like this. This exists on its own. I can use it for several different things. So here's what this thing looks like. So that's not normal, right? It's not that far away from normal, but it's not normal. See, this is Jabba the Hutt. Okay. This is called the chi-square distribution. This does not mean take the square root. That's a part of the symbol. It's just a part of it, chi-square. For those of you who might be interested at all, this is basically like taking a z-score form and folding it on itself. That's actually related to why it's called chi-squared. It's like taking this and folding it over and multiplying those together. That's how you get that shape.
it's like below the mean or above the mean.
True, but this... Okay. Does everybody kind of get why it's not shaped the way normal distribution? Because it's a graph that could represent standard deviations. That's one use for it. So I could get a group of people, calculate the standard deviation. Get another group of people, calculate the standard deviation. Over and over and over and over and over, and I'll end up with this picture. The same way I would end up with this picture if I took people's heights and plotted them out. It should be close to a normal distribution because heights are normally distributed. Standard deviations are distributed like this. This is not normal. Maybe. Okay, so the first use of this for us will be something called a goodness of fit test. Okay. Every time I say this, it's like, did this person who came up with this title speak English? I don't know. Goodness of fit. Well, that's the name of it. One major difference. Do you see how I drew this? I have a definite thing here, which means this is the what mark? This is 0. So that's a huge difference from this. Where's 0 on the standard normal distributions? Right in the middle. But again, I folded this. And then it goes forever up, right? So the chart to look up chi-square scores will be very different. It just will. This is not a normal distribution. It starts at frickin' 0. You're not going to have 1.645 and negative 1.645. You can't have any negatives. Yeah, it's squared. Yeah, it's like z-scores multiplied by themselves, basically. Okay, maybe. One other little thing that's not going to be too prevalent for us is the actual shape is determined by the degrees of freedom. And you can look in the book for different degrees of freedom. They all basically have the shape, unless your degrees of freedom is 1. If your degrees of freedom is 1, how big of a sample did you take? 2. And then things get really freaky when you only have 2 sample size, right? Okay, so the first thing we use this for is something called goodness of fit. So number one is, what the hell could that mean, goodness of fit? So let's say, is that the example I used already? Oh shit, that's back in the office. Damn. All right, I gotta run back to the office in a minute. Oh, it's on the other side of your thing. This sheet here. Okay. I think, what's the first example I do? Beautiful. M&M's. Okay, so let's look at this first example. Don't worry about the equations and all that shit. Just look at the table. So, if you got a bag of M&Ms, is there any reason to suspect, unless you happen to do this already, but if you went in with no expectations, how would you expect there to be more browns, blues, reds, yellows? Would you expect there to be more of any of those than the other ones? So you would expect there to be a uniform distribution. So two things can happen with these problems. Either I can say that they're uniformly distributed is what we expect to happen, or I could tell you what percentages I expect to fall into place. Right? Another example I like to do is grades in a class. I expect 10% to make an A and 25% to make a B, whatever. So the reason we call this goodness of fit is I have an expectation of what things are going to look like. And then I actually go and frickin' look at it. I get a bag of M&Ms, dump it out, keep everybody away, don't eat any myself, and just count the number of each color I see, right? So that's the first two columns, isn't it? This column is what I expect at. If I have 42 M&Ms, and I expect it to be uniformly distributed across the 6 colors, of course I'd expect 7 per each, right? 42 divided by 6 is 7. I like it. Let me stop here for a second. So if I say we think it's uniformly distributed, okay, you take the total and you divide by how many categories there are. Because that's what each one is going to have if they all have the same amount. Now, is it true that they all had the same amount? What was there the most of? Blue. Because it's the biggest number. Right? You guys all right? You guys all right? You're all like, I don't know what this shit is, man. You're talking Jabba the Hutt and friggin' zero and bullshit and folding and what the... All right. But just this. This is what we think would happen, and this is what actually happened. Now, just like hypothesis test, if I think the mean is 10, and I get a mean of 9, does that mean I'm wrong? No, because where did that 9 come from? A sample. So I can't just go immediately go, huh, you're wrong. You're full of shit. I can't do that because I know these are different. So what do you think the whole point of this test is going to be? Is that difference big enough difference? The same way, like, if I find evidence, I got to find enough evidence. I've got to go out in the rejection region. I've got to really be far away for there to be evidence that it isn't equal to this. So here, what I see has to be really different from what I expected. So obviously, one of the first things I'm going to do is take the difference between what I see and what I expect. Right? That's the whole point of this. Let me stop right now. Some of you guys are looking down at your desk. Oh, I'm sorry. Stay with me. This is actually not that horrible. Okay, so if I did see a bunch of 7s here, if I actually saw this exactly, then I'm like, well, there's awesome evidence I'm right. Well, there you go. Right? And then what would all these be? These would all be 0s. So what's going to happen is I'm going to use that picture. If I get 0, that means that they were lockstep with each other. That's not evidence they're different. In fact, that's really good evidence they're the same. So I have to get a difference that's far enough away from no difference. So it feels a lot like our hypothesis tests. You're not going to have to do all the steps. Don't worry. I'm going to show you exactly what you have to show me and what you have to say. Okay. So why do you think I square the differences? Do you remember when we did standard deviation? Why did we have to square stuff? Yeah, because they got negatives and positives, they all cancel each other out. So that's stupid, right? So we square this. And then, now here, what does this kind of do? So for each one, this is the squared difference, right? But then I kind of normalize it to what I expect. I divide by the expected. So so it's like, okay, how big of a difference is this? Kind of depends on, well, what did I expect to get? If I expected 8,000, then this is not that big of a difference. So when I divide by the expected, I'm kind of getting a relative feel of how big that difference is. Okay, maybe. Do you have to really understand what I just said? No, it's just a freaking formula, right? You're going to plug shit in and do your thing. So here's what chi-squared formula is. It's the sum of these. And I got 3.143. Now, all right. Let me stop right there. So that 3.143 is a gauge of how relatively different that bag of M&Ms was from what I expected. Now, right now, you have no idea necessarily how big a deal 3.143 is. But what would your gut tell you? Does it sound like it's a big difference? So we don't know yet, right? Good point. You're like 3.143 z-score would be a huge difference, wouldn't it? But this is not a z-score. This is different. So let me do this. I need to go back to the office real quick and grab these tables because I need to be able to look this number up, just like we did with z-scores. I looked at the z-score critical, and then I calculated the thing from my sample. So I'm going to look up a chi-squared critical from the chart, and then I'm going to calculate the one from my sample and see where it falls. So let me do this. Let me let you guys, don't necessarily write anything down yet. Read through this and try to see what would go where. I just want to give you something to do while I run and get the charts. All right, read through this second part and see if you can figure out what would go where. I guess, well, I can leave the video running so I can hear what you
Alright. Let's see. Alright, let's see how to read this weird-ass chart.
I have to apologize for my statistics brethren. I don't know why they did this, but remember the z-score chart tells you the area to the left of what you look up? Do you remember that? Below. Okay, that's number one. Is they decided, yeah, let's screw with them. Now let me see, I haven't done this in a while. What would the z-score be? If you have a z-score chart, what z-score, well, I should be able to figure this out. I think it's 1.282, yeah. It's got 0.10 in that one tail. You can actually look at my t-score chart. Somebody do this for me. What's 1.282 times 1.282? Let me see if I remember this correctly. Darn it, doesn't do what I wanted it to. Oh well, I'll let it go. Why doesn't that work exactly right? Too bad for me. All right, I got to think about why this. I haven't done that in a long time as to how to do the folding and to show you on this chart, so I'm not going to worry about it right now. So, for this first problem, we'll talk about the second problem in a minute. For this first problem, do you see that chi-squared critical? All right, so the very first thing we got to figure out is, how do I get degrees of freedom? Degrees of freedom is not 41. The degrees of freedom for goodness of fit is related to the number of categories. How many categories do we have? 6 minus 1 is 5. So in this, I think they use K, not N. K is the number of categories. Let's just stretch it all. So you don't do 42 minus 1. You do 6 minus 1. So if you look at your chart, look at degrees of freedom of 5, right? Degrees of freedom of 5. And I'm using a 0.05 level of significance. So we look up here, 0.05, degrees of freedom is 5. There's the 11.071. Ooh, which is what I got here, right? So what that looks like then is little Job of the Hutt, dude. Oh. And I've got to get to 11.071 to show evidence that they are different. Because this chi-square formula, there are other chi-square formulas. One of them deals with standard deviations, which makes sense. Just like there are multiple z-score. There's one that deals with means. There's one that deals with percentages. You guys with me? Same kind of idea. This chi-square score tells me how different what I see is from what I expected. So the difference between those two has to be at least this to show evidence that they are different. What did we get? Or what did I get? I got 3.143. Remember, what's this? What's right here? 0. So 3.143 is like right there. So is that evidence that they're different? No. So right here, we have not found evidence to reject the claim that they're uniformly distributed. We didn't find evidence that they're different. You could say it that way too. You can use like normal English. Okay. I'm not going to be overly picky about the way you word this. How would I find evidence that they are different? I'd have to be out here. They have to be so different because it's only a sample. So it's got to be really different to be evidence. Maybe. So let's get this going together, and then I want you guys to finish it out. Some of you guys already have finished it out. Let's start with observe, because that's the easy one. There's a lot of numbers running around this problem, so you got to be careful. So how many had a below 130 level of blood cholesterol? No. This is what I expect. How many did I see? 120 had below 130. How many had between 130 and 200? 240. How many had between 200 and 400? 100. How many had more than 240? The rest. And there's 500 total. Yeah, so 3, 4, 60, so 40. me stop there. Is everybody cool with that? That's just, so observed are the actual things I saw happen. Now, what do I expect? I expect it to follow this pattern for the general population. Or that's what I'm testing it against. And do you guys understand? Do you remember, well, did your mom ever, or some of you guys are the mom, I'm talking about this example, but you ever heard of the Mediterranean diet? Right now, you got the paleo diet or whatever. Yeah, really. The Mediterranean diet was because we saw that people living around the Mediterranean were all like fit. What's going on there? Probably they walk more than people. But we looked at their diet and we're like, olive oil. Olive oil. Everybody just started guzzling olive oil. Make me no, it won't. Just stop it. But this is what we do. We go in, we say, here's what everybody does. Let's look at this group. Does this group follow the pattern? And if there's evidence that they don't, why? Do you guys follow? So this is just preliminary study to see if they follow the general pattern. And if I find evidence they don't, if I find evidence that they're better, then I'm going to go, okay, what do you people do? Do you walk a lot? What kind of stuff do you eat? What's in the air? What's in the water? You know, like, come on, tell me. Is it all genes? Are you all related? Is it all genes out? Right? I dig deeper. So, how the shit, what percentage do you expect to have less than 130? 20%. 20% of 500. So, how would I figure out what I expect for this? What's 20% of 500? 0.2 times 500. What's that? I think I heard somebody say it. 100. So expect 100 to have less than 130. They're already looking a little bit better, right? Because the lower, the better. At least for the bad, the HDL. You guys kind of with me? What's 30% of 500? 150, I like it. So everybody see where these numbers are coming from, right? So these are the two main ways. Either I say they're uniformly distributed, in which case you just divide how many there are by the number of categories, because every category is going to get that many. They all have to be the same. Or I expect this percentage to be here, this percent, and then you just take that percentage of the total and plop it in, right? So for 200, 240, it's 35%. What's 35%? Yeah, 175. And then finally, what's 15%? Huh? 15% of 500. Is it 75? Why did I put 100 here? That's what's throwing me off. There we go, Jeff. 75. So just do the percentage of the total amount I'm talking about. Does that make sense? That's what a percentage means. So it should make sense. So just eyeballing these, do they look very different? Yes. So I kind of expect maybe we're gonna find evidence that they are different. So now go ahead and finish this out if you haven't done so already. Just take the difference and then square it. Square it. You could do this in L1, L2, L3, L4 if you wanted to. You just build the equations. Oh shit, I don't know what 75 squared is. Thank you. 100 divided by 4 is 1, 2, 2, 5, 12, 25. So that's kind of like the raw difference. And then I want to make it a relative difference. Because again, if I said two things are 8 million apart, does that sound like they're very different? If I said two things are 8 million apart, does that sound very different? What if I was talking about 80 trillion versus 80 trillion and 8 million? I mean, that's not very... So if I divide by E to get a sense of how relatively big is that difference I'm talking about. So this last column is just going to take 400 divided by E. What's E for this one? 100. So you get 4. That's amazing. Then you do 8100 divided by its E, which is 150. And you get something. What do you get? 54. And then you do 625 divided by 175. Let's do it again, sorry. 32.14. Is everybody seeing where everything's coming from? So I do this difference divided by its expected. 1225 divided by 75. 16.3 repeating. I love it. And then I add all these up. Because what's chi-square? It's the sum of all these things. Get out of there, extra line. So let me add all these up. 58, 90.14, 106.44? I don't know. Is it? All right. So that's kind of like, I wouldn't call it this because that'd be crazy, but this is like chi-square star. It's like Z star. Is the one we calculate from our sample. Now, can you take a minute and look up the chi-square critical? How far away is it we're supposed to get? 0.01 level of significance. How many categories are there? 4. So you know what the degrees of freedom is. Try to see what this score is relative to like this one up here, the 11.071. Find the one for this one. Put 0 to 1, level of significance. The degrees of freedom is 3, so I get 11.345. And we got, from our sample, we got 106.44. So we're like way out there. So did we find evidence? Let's try this again. Did we find evidence? Oh shit, yes. Where's our rejection regions? Like in here. So either I get far enough away and I find evidence, or I don't get far enough away, which is not enough evidence. So we have found enough evidence to say what? That these people's cholesterol levels are the same or different from the general population. What was it? So which one? You got a 50-50 shot. What does 0 mean? If I got his chi-square 0, what would that mean? The only way to do that is if my expected and my observed are the same. So that's the closer to 0 I am, the less evidence they're different. Let me say it that way. And how far is far enough away from 0 to show evidence that they're different? That is. And what do we get? 106. So we have found evidence that these guys are different. Their cholesterol levels are different from the general population. That is enough evidence. That is way big time evidence. Then I would go in and study more specifically. All right, well, what do you guys eat? Let me get all the people that don't eat this and the people that do eat this, and let me see how different your cholesterol levels is. You know, and if they are very different, maybe it's that thing. And if they're not, no, it's not that thing. Let's try something else. Yes, yes. So a lot of what we do in Stats 1 is like the intro analysis. It's just quick, rough, dirty intro analysis, and then I go, oh shit, I better get in there. I see something. Let's go figure out what it is. I don't know it. Don't just start guzzling olive oil. We don't know if that's what it is. Well, that's disgusting. All right, maybe. Now this is section, did I put it up here, 11.2, right? Section, yeah, 11.2. 11.1 is just basic stuff about chi-square distribution. So I'm going to let you read through that. To be honest, that's all I really wanted to do today. Right, that's kind of crazy. Yeah!
Go you.
Oh, sure. I'm such a good teacher. I'll let you out early.
Who you?
There you go. That's better. Please don't forget your ID. Thank you. I've had people do that.
I just did it and none everywhere else. I literally lose my ID on the ring. Dude, I know. RTV's been not doing my ID. She just turned 21. I know. So it's time for me to get it back. I didn't say happy birthday. I didn't even say that. I just thought it was birthday. I should take her out for a drink. Mike's gone all weekend, so I'll take her out for a while.
Sure, the car keys do it have. It's a BMW, am I? You guys
I have $20 on Untitled Chapter for the manager. He gave me an Alpine car to Chapter. Oh, you think I'm allowed to go leave it, girl? She likes it. Yeah.
Wait, when's the quiz on?
What?
The quiz? You said that was gonna be one more quiz, right?
Yes. We haven't talked about it yet, so it's not next time yet.